In this module we will use what we have learned about motion on a straight line and apply them to motion moving in two or more axes. If you ever been on motor track races, you may have seen a sport called motocross. Shown in the figure is figure of the motion of a biker jumping from one point to another. The biker appears to move in both horizontal and vertical axes. This is an example of an object or projectile moving in two dimension. The path traversed by the biker or the projectile is what we call the trajectory. Projectile motion can be observed and demonstrated easily by anybody. When you play games such as basketball, tennis, or any type of sport that involves motion of projectile traveling in a two-dimensional plane. In this chapter we will examine this type of physical phenomena and look at the details in solving this type of problems. Shown in the figure is a graphical representation of a projectile motion. As you can see, we use vectors to denote the magnitude and direction of a projectile. The blue lines represent the vector velocity while the green and red colors represent the components of the vector. We also see a solid orange color arrow. It represents the acceleration of the projectile. The acceleration represents the acceleration due to gravity. So the scenario in this figure shows a projectile launched at a reference origin with an initial velocity called v0. The projectile moves in a two-dimensional plane and reaches a height h, which suggests that the velocity along the y-axis is 0 and the velocity at the top is equal to the velocity along the x-axis, or v is equal to vx. After reaching the top, the projectile begins to follow a trajectory leading downwards, so the velocity along the y-axis becomes negative values. Examining the y component of the vectors for both going upward and downward, they appear to have the same magnitude but opposite in direction as long as they are at the same height. Similarly, we see that the x components of the velocity vectors for both going upward and downward, they appear to be the same all throughout, which suggests that the acceleration along the x-axis is 0. The physical significance of the acceleration along x-axis having a 0 value suggests that the experiment is done in a vacuum or the air resistance has been ignored. The assumption of air resistance being ignored is typically done to simplify physics problems like projectile motion. Recall the equations of motion along x-axis. Incorporating the given assumptions and conditions of the projectile motion, we can simplify these equations to fit the conditions needed for a projectile motion. We note that the acceleration along the x-axis is 0, the velocities along the x-axis are the same, or v0x is equal to vx. We see that upon substituting the conditions along the x-axis, the equations motions are reduced to two equations for motion. This is because the projectile's motion travels across a plane where acceleration is 0. This is possible if the air resistance is ignored or experimentally done in a vacuum condition. Which we see that for acceleration equal to 0, then the velocities along the x-axis are the same all throughout. Now let us look at the equation of motion along the y-axis for a projectile motion. Recall the table for the equations of motion for objects moving vertically, where the value of g is equal to the negative 9.8 meter per second square. We see that all of the equations are retained for projectile motion. Here we summarize the equations in solving for the projectile motion problems. And we apply Pythagorean theorem to solve for the magnitude part and tangent function for the direction of the velocities. For projectile motion having a parabolic-shaped trajectory where its initial position is equal to its final position along the y-axis as shown in the figure, we can directly solve for the height and range of the projectile, using the equations shown. Let us look at this example. A bullet is fired horizontally with an initial velocity of 245 meters per second. The gun is 1.5 meters above the ground. Letter A, how long is the bullet in the air? Letter B, if the rifle is tilted 10 degrees with respect to the horizontal, what is the maximum height reached by the bullet? Note that air resistance has been ignored, so we can assume that the acceleration along the x-axis is 0 and the velocities along x are the same. First we draw the problem to better visualize. We can also determine from the figure some of the parameters. So we set the initial position as the point where the bullet or the projectile is released. By doing that we can set the initial positions x and y0 to 0. We know that the first scenario the bullet is released horizontally, so therefore the velocity along y is 0. We also know that the air resistance has been ignored, so we can set that the velocity along x are the same. We see that at the point of release the value of the initial velocity is 255 meter per second, which is also the velocity along the x-axis. The second step, we compare the given values obtained from the figure with the equations of motion for a projectile motion. Here we see that the equation number 5 contains the necessary physical quantities to solve for the unknown parameter t, or the time of flight of the projectile before it hits the ground. So for the first question, the time of flight of the bullet launched horizontally at a 1.5 meter high is equal to 0.56 seconds. We note that we ignore the plus or minus sign for physical quantity time, since it is a scalar quantity, or in other words it's simply the magnitude. For the second problem we again draw the problem to better visualize. We can also determine from the figure some of the parameters. So we set the initial position as the point where the bullet or the projectile is released. By doing that we can set the initial positions x and y naught to 0. We know that the second scenario the bullet is released from an angle theta equals to 10 degrees with respect to the x-axis. We also know that the air resistance has been ignored, so we can set that the velocity along x are the same, so all the velocity along x are the same. At the maximum height the velocity along y is 0 before the projectile descends. By examining the figure we can see that it forms a perfect parabola, so we can use the direct equation to solve for the height. Using the direct equation to solve for the maximum height reached by the projectile and the value for the initial velocity, we get that the maximum height of the projectile is 100.04 meters above the point of release. Do not forget to write your solutions clearly and box your final answer. Average and instantaneous velocity. As a projectile moves in space, its velocity is measured as the change in position over time. For instantaneous velocity it is a measure of change in position over a very small change in time, or close to 0. So it is quite difficult when a projectile moves in a path that allows changes in direction, such as a curved path shown in the figure. Instantaneous velocity is also expressed as a differential derivative of the position over time. From there we can also determine other types of physical quantities, such as instantaneous acceleration, which is derivative of the velocity over time. For projectile moving over a curved trajectory where it starts at point P1 at a time T1 defined by a vector position R1 relative to an origin point, then moves to a different position P2 at a much later time T2 defined by a vector R2, the velocity measured is the average velocity. In actual systems such as the velocity measured by a speedometer in cars, it is actually an example of an average velocity. Let us look at this problem, which is still moving in two-dimensional space. So a particle or a projectile has a position vector r equals 30t I hat plus the difference of 40t minus 5t squared j hat, where r is in meter and t is in seconds. We are asked to find the instantaneous velocity as a function of time for letter A, and the second one is to find the instantaneous acceleration vector also as a function of time t. Solving for the instantaneous velocity, we simply take the first derivative of the position vector and we get an expression for the instantaneous velocity as a function of 30 I hat plus the difference of 40 minus 10 t j hat. Similarly, for the instantaneous acceleration we take the first derivative of the velocity vector which we previously obtained in letter A. We get that the instantaneous acceleration is equal to negative 10 j hat. Or you can also take the second derivative of the position vector r. Do not forget to write your solutions clearly and box your final answers. In this problem we ask to find the velocity vector and position vector given at different times. So, a particle moves in an x and y plane with constant acceleration. At time t equal to 0, the particle is at x position equal to 4 meters and y position equal to 3 meters. The acceleration is given by the vector a equal to 4 meter per second square I hat plus 3 meter per second square j hat. The velocity vector initially is v equal to 2 meter per second I hat minus 9 meter per second j hat. First step is we extract the values that are known. So for the first case we add the time parameter to the known values and from by a different time parameter to the known values. Note that the initial positions can be re-expressed in vector form as the summation of its components. So rewriting the initial position as r naught equals to 4 meters I hat plus 3 meters j hat. So comparing the equations of motions to the variables that are known, we see that the first equation can be used to determine the expression for the velocity vector at time t equals to 2 seconds. For the second problem, we see that the position vector can be obtained using the third equation. Using the first equation and substituting the known values, we obtain that the velocity vector at time t equals 2 seconds yields 10 meter per second I hat minus 3 meter per second j hat. For the second problem, we substitute the known values and obtain the position vector at time t equals 4 seconds. Here we get that it is equal to 76 meters I hat minus 9 meters j hat. Do not forget to write your solution clearly and box your final answers. The end for now. For questions and comments, you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at @dies learningstuff. Note, please do not forget to use your school email. Also write your complete name and class section. Thank you for listening and see you next module.